Hi, we are Group 42. In this video, we will be taking you through our analysis on the Store Item Demand Forecasting Challenge from Kaggle. For this challenge, we are tasked to predict future sales for the next 90 days for a selection of 50 items across 10 different stores. This challenge is based on a rich dataset comprising 5 years of sales data. The main challenges in this project include dealing with seasonality in the data. We have to come up with a model that captures patterns and seasonality of the data. Another challenge is the huge store item combinations. With 10 stores and 50 items, this translates to 500 store item combinations. Do we have to model these combinations individually? Or can we leverage on the interdependencies between stores and items? To answer these questions, we will first carry out exploratory data analysis to uncover interesting patterns and trends in the dataset. Over here, we have a line plot which shows the aggregated weekly sales across all stores and all items between 2013 and 2018. Total weekly sales is plotted instead of total daily sales as it gives a clearer visualization of pattern. The line plot reveals a yearly seasonality on weekly sales, and the 52-period simple moving average shows that total weekly sales has an overall increasing trend. To check whether the seasonality and trend patterns exist in each store, we also plot the total weekly sales by store. To our surprise, all stores seem to enjoy very similar growth in their total weekly sales. This is supported by the correlation matrix, where you can see that each store's weekly sales are strongly and positively correlated with one another. Plotting the total weekly sales by item, we can also see that all items generally enjoy a very similar growth in their total weekly sales. Similarly, the correlation matrix shows that all items' weekly sales are strongly correlated with one another. The graph here shows the contribution of each daily sales to the weekly sales for each week. We can see a consistent trend of increasing sales across each day of the week except for Wednesday. From the different lines representing different weeks, we can also see that this upward trend is consistent throughout the year. With the exception of week 50 to 52, where it seems that the sales are more evenly spread out throughout the week. However, our prediction problem is for the first 3 months, so we will not be focusing on this. Next, we have a plot that shows the density of each daily sales contributions to weekly sales. The horizontal axis represents the percentage of weekly sales a specific daily sales contribute to. The peaks on the density plot suggests that a large proportion of daily sales contribution are concentrated on a specific range of values. Wow, that must have sounded a mouthful. To give an example, let's look at day 1. It has most of its sales percentage lying in the range between 0.1 and 0.12, suggesting that day 1 generally occupies 10 to 12% of the weekly sales. Given this information, we may be able to find the total daily sales for each day of the week with high precision if we can accurately forecast the total weekly sales. Where given an accurately forecasted total weekly sales, we can multiply it by the average percentage to get the total daily sales for each day of the week. As the density for the daily sales contribution is normal-like, we take the mean of the percentage, which is approximately the percentage with highest density as the daily sales ratio. Plotting the autocorrelation of the percentage of weekly sales for each day, we can see that the percentage of weekly sales for a certain day is highly correlated to that from the last year, for example day 0, which is Monday. This suggests a yearly seasonality pattern. We also investigate how much each store contributes to daily sales throughout the years via the percentage of total daily sales shown in the y-axis. One interesting trend that we notice across all items is that all the lines are almost horizontal with extremely small fluctuations, approximately plus minus 0.3%. This suggests that we can take each store's contribution to daily sales as constant throughout the period. This is further supported by the autocorrelation plot for each store. The low autocorrelation for all stores suggests that each store's contribution to daily sales is time independent. Similarly, we investigate how much each item contributes to daily sales throughout the years. Likewise, we notice that all the lines are almost horizontal with extremely small fluctuations, approximately plus minus 0.3%, suggesting that we can take each item's contribution to daily sales as constant throughout the years. Similarly, this is also supported by the autocorrelation plot for each item. Summarizing the previous findings into an equation, we are able to predict a specific daily sales for a specific store and item. Given the predicted weekly sales across all stores and items, multiplied by the average daily sales ratio for that day, and the average store ratio for the specific store, as well as the average item ratio for the specific item. However, there are a few assumptions that need to be addressed before we use the equation for calculation. Firstly, we assume that store-wide contribution to the daily sales is the same for every single day of the week. This presumption can be supported by the graph here, which shows that each store's contribution to the daily sales for every single day of the week is pretty much constant. Another assumption is that we presume item Z contribution to the total daily sales is the same for every single store. This assumption is supported by the graphs above. On the left, we have the density plots of item 1 contribution to total daily sales of each store. We can see that the density plots for all the stores overlap with one another to a great extent. This suggests that item 1 contribution to the total daily sales for every store seems to be about the same. A very large proportion of their contributions lie within 0.3% from the peak of the distribution. This pattern repeats when the same density plot is applied to all the remaining items. This consistency allows us to make a generalized statement that given any item, its contribution to the total daily sales across all stores is likely to be similar. This gives us the confidence that the equation will provide a close approximation of the actual daily sales for each item in each store. Now, we will talk about our approach to forecast our daily sales. With the insights we derived earlier, we will use the equation shown on screen to model and predict daily sales for each store and each item. Let's take a closer look at how this equation will guide our predictions. To predict weekly sales, the total for all items in stores within a specific week, we're using linear regression and SAR-AMA models. We'll compare their performance to find out our best forecasting tool. To obtain daily sales from the weekly sales, we will multiply the predicted weekly sales with day X ratio, which is the average percentage of weekly sales for a specific day of the week. To drill down to the sales for a specific store and item, we apply store and item ratios, which show their share of daily sales, pre-computed from our training data. We also explore other techniques that model store and item sales individually to ensure we choose the most effective method for our sales forecasting. We will now go through the models that we have selected and how we implement them for our forecast challenge. First up, we have linear regression. It is a statistical method used to predict a dependent variable based on one or more independent variables. It assumes a linear relationship between dependent and independent variables. For our case, however, we implemented polynomial regression, more specifically second-degree polynomial regression, to capture the nonlinear relationship between the dependent and independent variable. In our regression model, the idea is to calculate the total sales of the first week of each year and fit a quadratic polynomial, degree 2, to the data. Plotting the actual and predicted values to check our results, we can see that our predicted values lies closely with the actual values. Subsequently, we will multiply the forecasted total weekly sales with the calculated ratios of the sales per item, store and day. To obtain the total daily sales for each item each store is shown on the table. One of the disadvantages of using this model is that it could be too simple as it does not take into account unique characteristics of time series data such as seasonality, as shown at the graph here. Next up, we have SAR-AMA, which stands for Seasonal Autoregressive Integrated Moving Average. It is a technique of ARIMA, where the seasonal component can be handled in univariate time series data. Seasonal ARIMA combines both non-seasonal and seasonal components into a multiplicative model. For the non-seasonal part, an ARIMA model is P, Q, D, which are the orders of the autoregressive, integrated, and moving average terms respectively. More detailed explanation regarding these components could be found in our documentation. But to summarize, the AR part looks at how past values influence the current ones. The I part helps to do trend differencing to ensure that data is stationary. And the MA part looks at the lags in the white noise. For the seasonal part, it can be represented by capital P, D, Q and M. Capital P, D, Q are the additional hyperparameters that are similar to that of AR-AMA, but are for the seasonal components. And M is the periodicity of the seasonality. Our exploratory analysis showed a clear seasonal trend, with sales typically rising at first half of the year and falling at second half of the year. To capture this pattern, we set our SAR-AMA model seasonality parameter M to 52, reflecting the annual cycle in our weekly data. For the rest of the parameters, they can be determined by using the PM-DARIMA auto_ARIMA function, where it optimizes to find the lowest ACK information criterion. After we obtain the optimal parameters, we plug them into the SAR-AMA model and make weekly sales forecast 90 days into the future. Then, multiplying it with the calculated ratios of the sales per item, store and day. We to obtain the total daily sales for each item each store is shown on the table. We also try out another approach where we directly forecast the daily sales for each store and each item. We will show the results later in the video. Lastly, we have Profit, which is a forecasting tool created by Facebook. We included the Profit in our experiments because of its strengths in handling time series data with complex seasonal patterns, like yearly, weekly, and daily seasonality, as well as holidays. It uses a decomposable time series model, where it can be broken down into G, T, the function that captures trend, S, T, the function that captures seasonality, H, T, the function that captures holiday effect, and Epsilon T, which captures the random noise. In our approach with Profit, we decide to shift our strategy. Instead of relying on the correlations we identified earlier, we directly forecast daily sales for each store and each item. This allows us to explore a different angle in our predictive analysis and allow us to do comparative analysis between different approaches. Finally, we will now bring you through the results of our analysis. Over here, we can see that the methods leveraging on the ratios in the equation we identified earlier clearly outperforms those that model the sales of each store and item separately. When we analyze sales by modeling each store and item separately, we simply treat them as independent entities, ignoring potential interdependencies. By accounting for the dependencies between stores and items, we find that a simple linear regression model can outperform advanced models like Profit, which do not consider these dependencies. While linear regression outperforms other models in our analysis, it's important to recognize its limitations for time series forecasting. Firstly, it doesn't account for time series characteristics like seasonality. Secondly, since it is a second-degree polynomial, it will reach a maximum point and will strictly decrease after that point, leading to unrealistic forecasts. This limitation becomes more pronounced with longer prediction windows, making linear regression more suited for short-term forecasting. With that, we have come to the end of our video. Thank you.